Hey folks, how's it going? Hope you're doing okay amidst the crazy windstorm that's happening behind me. I don't know if you can see my, oh, it doesn't look that bad. Um, it sounds pretty bad. Anyways, uh, continuing on, last lecture for the week here. I'm going to try to keep this one fairly short. So let's get the timer going. Okay, so in the last video, just to keep up with reviewing these learning goals, we went through the 1D time-independent translational motion Schrodinger equation, and we're going to keep discussing the Schrodinger equation ad nauseum, and we're going to keep adding more of these qualifiers to it, such as three-dimensional. We're going to build in more than just translational motion. We're going to build in vibrational motion, rotational motion, etc. So I'll highlight this, but recognize this that, let's see, highlighter, that we're going to keep continuing to talk about Schrodinger. And then we talked about how to solve second order differential equations, okay? So I'm going to keep continuing along with these learning goals. Okie dokie, let's put this away. Fantastic, okay. So we came up with this equation last time, if you recall, okay? Don't shift around on me. So, and that was from solving this standard second order differential equation. And we came up with that we can use this exponential form, or using the Euler relations, we could use sines and cosines. And it's important to note, as we're going to see, this isn't exactly an accurate realistic wave function because it's one-dimensional and it's time independent, but it's a good start. It's a good start for us, especially getting used to these mathematical operations. Okay, so for example, I'm going to play with this exponential form. And if we just simply ask the question, where is the particle? Okay, where is the particle? Well, we know now that we can take the square modulus to find it, okay? And so I'll remind you that square modulus goes as psi star, so I'm going to put the sub x there so we remember 1D, psi star psi, which we remember is the square modulus, okay? And I'm not going to worry about integrating this. Let's just take the square modulus of this initial wave function that we've come up with and see what happens. And for now, just to make life easier, I'm going to play a game where we say, suppose b equals 0, okay? So again, this isn't accurate, but it's going to give us a good means of getting used to this mathematics, okay? So then if b equals 0, we can say psi x just equals a e I k x, okay? And if I go and take the square modulus of this thing, so I remember that what I'm going to be doing, I'll fill in this notation, it's going to be a e I k x, and the conjugate of that, that's star, okay, times the wave function, right? So I'm just filling that in, psi star psi, okay? And so all of that is going to equal the following. So we'll say A star, and then when I apply the conjugate to that, that's going to be e to the negative I k x, okay? And then that's going to be times a e I k x, okay? Well, what do I get out of this? Well, e to the negative I k x times e to the I k x is 1. And we know that that a has to be a real number. It's a constant. So this just turns out to be a star a, which I will just write as the square modulus of a, okay? And as it turns out, because there's no x dependence, this isn't exactly a realistic wave function, okay? So with the square modulus of this just being equal to some constant, it implies the wave function can be found everywhere simultaneously with equal probability. So in other words, if I were to normalize this wave function, okay, we know that with the normalized wave function, it's n squared integral of psi star psi dx all equals 1. Well, if my psi star psi is just equal to this a squared, and then I go to normalize it, then that whole thing is just equal to 1, as this indicates right here. And that implies the wave, or the particle, can be found everywhere with 100% probability. And that's just not realistic, okay? And so an interpretation of that e to the ikx, that would be made up of a real component that's a cosine function and an imaginary component that's a sine function through that Euler relation. And so if I add those two waves together, I get this uniform constructive interference. Okay? Well, what if we supposed that A equals B? Okay, so we have this scenario. Let's look at this scenario. Okay, so then I could write psi of x equal to A, and then that would be, so if we know that A is equal to B, then I'm just going to substitute and collect like terms. E to the ikx plus e to the negative ikx all times A. Okay. And so I'll also note that, and I'm not going to go through this in great detail, but through Euler, this would actually all be equal to 2a times the cosine of kx. Okay, these two exponential functions. And then now, if I were to carry out the square modulus on this 2a cosine kx, okay, when I do there's no imaginary numbers in this cosine function, all right? So the square modulus of this will be truly just a square. So that will go as, right, 2 squared, a squared, cosine squared. It's all squared, okay? So that will be 4 times the quantity a squared times cosine squared kx. And this is looking like a much more reasonable wave function and probability distribution because there is an x dependence. And so that's what this graph is right here. So my cosine kx function looks like this one that has the negative values, okay? And once again, where it crosses the origin, we call those nodes. And where it peaks, those are most probable places of finding the electron. And so the cosine squared graph looks very similar to the cosine graph, except for it's a little bit narrower, and obviously because it's squared, it doesn't have negative values. Okay, so what we're kind of starting to get at are more of these kind of guidelines of what should be acceptable wave functions. Okay, all the same, we're still going to play with this, you know, what I'll call trial wave function, ae ikx plus be negative ikx, as a means of feeling our way around this quantum mechanics. Okay. So, operators. We've been talking about operators. Let's talk about operators some more. Okay, so I'll remind you, this is the general form of our Schrodinger equation. So, right, we know that that was h psi equals e psi. Okay, so here is a general form of an eigenvalue equation. And right, the way this works, the operator operates on the eigenfunction. And what we get out of it is the eigenvalue and the original wave function. Okay? And of course, if we used the Hamiltonian total energy operator, then the eigenvalue we get out is the energy. Okay? So for example, energy operator operates on psi, returns energy. Or if I did the, let's say, position operator operating on psi, that would return to me the position, and of course the original wave function. All right? So for example, let's play with an example here. All right? Let's suppose, let's see here. I'm going to write this up in the general version. And so this is an uppercase Greek letter omega. And recall we put a little hat on it to note that it's an operator. Operator operates on psi and returns. This is not a W, it's a lowercase omega. And so that's our eigenvalue, which is a real number, a real single valued number. Okay? So let's suppose that my operator is d dx. So first derivative of position. Okay? And once again, these aren't necessarily physically accurate operators and wave functions. We're just playing with the math. And let's suppose psi equals e to the ax, okay, where a is a constant. So what is omega? Let's find the eigenvalue. So now when omega operates on psi, I can write that as d dx of e to the ax, okay? And that all equals a e a x, okay? Which equals, right, we know psi is e to the ax, so all of this just equals a times psi. Therefore, a is our eigenvalue. And this works beautifully. This operator and this wave function would be valid operators and eigenfunctions, excuse me. So psi is the eigenfunction. This would be a valid quantum mechanical operator, okay? So, but now, let's see, I have another example we could do. Okay, so suppose now that we still have this same operator. Okay, so I'll draw a line here, so we're gonna move on. I'll say this is example 1 on operator. Let's do example 2. So we'll still play with the same operator, d dx, but now let's suppose that psi equals EAX squared, okay? So now if I operate, let's see here. So now if I operate on psi, okay, so that's d dx e to the ax squared, okay? If I now carry out this operation, so recall when I take the derivative of this exponential function, I'm going to take the derivative of what's in the exponential and then put it out in front. So the derivative of ax squared becomes 2ax, and then the original, right, the operation then dictates that that would have to be 2ax e ax squared, which would then equal 2ax times psi, because EAX squared was psi. Okay, so this is not an eigenvalue because of the x, right? We recognize x will take on a large number of values, okay? So we have to tread lightly. We have to tread, I guess I should say carefully, when looking at operators and wave functions, okay? We can only have operators that will give us eigenvalues, all right? So moving along, so let's do a more physically realistic set of operators with a somewhat still slightly realistic wave function, somewhat slightly being this, right, this 1D wave function. And I'm going to play the same game with a equals 0 or b equals 0, okay? So my, let's see here. So my linear momentum, right? If I want to know what is the linear momentum, so that's going to be the eigenvalue. And to get that eigenvalue, I have to use the operator corresponding to this linear momentum, okay? So the linear momentum operator, recall, is the following. H bar over I d dx Okay. And so now if I use this operator and operate on psi, let's do it for when b equals 0 initially. Okay, so we'll say this. And then so now we're just going to say suppose psi is a e I k x. Okay. When this now operates on the wave function, we're going to have h bar divided by I multiplied by the first derivative of psi. And I'm going to put some extra parentheses around here just so we recognize we're in the order of mathematics. We're first taking the derivative of this function, then we would multiply it by h bar over I. Okay. So let's see here. When I do that, just making sure I write down the right results here. Okay. We are going to get the following. So for the, I'm going to keep h bar I out in front for now. And we know that the ddx of a will just also come out in front. Okay. And then now ddx of eikx is just going to be equal to k, let's see here. Yes, it will just be equal to k I, right? Because those are the constants. Yes, ki and then e I k x. Okay. And so now what we've got going on here, the i's and the i's will cancel. And I have a k h bar e I k x. So what is that all equal to? Well, I remember that a e I k x is psi. Okay. So let's put all that together. K h bar times a e I k x. And we know that that's all equal to psi, right? So we can see my eigenvalue is, I'll circle it right here. Or excuse me, let's just make sure I'm writing this all down to completion. Kh bar, and then that's the original wave function. Beautiful. So Kh bar is a constant. It is an eigenvalue. Okay? So we could say then, I'll just write this succinctly, linear momentum of psi of x, okay, in this case equals, and I'm going to write the positive sign just so we know that we've got it there written down, okay, equals positive kh bar psi x. And so now if we were to do this for, so let's see, this is for b equals 0. If we were to do this for a equals 0, I'm just going to describe this briefly because perhaps as you might see where this is going to go. Okay? So when a is equal to 0, my wave function is just be negative ikx. And so now the only difference will be here when I take this derivative, right? I'm going to have that negative sign moves down in front. Okay? So try it for yourself. I'll just show you the result. It's negative k h bar becomes the eigenvalue, and of course, multiplied by the original wave function. Okay. We're going to come back to this result because as it turns out, there's physical significance to this result of getting these two different eigenvalues for linear momentum when either b is 0 or a is 0, given that they're equal and opposite. There is some physically significant results to this, and I'm going to come back to it next week in our lectures. Okay? So carrying along, and so we talked about general operators, we talked about the linear momentum operator, and now let's see here. I'm going to make sure I'm in the right position. Pun intended. Let's see. Aha, beautiful. Okay, so I'll remind you. Our potential energy operator, right? This is just kind of a reminder slide. Okay? our potential energy operator, we use this term V. And I've shown you in some cases we could use just a constant potential energy. As it turns out, a potential energy operator that we're going to see come back in Chapter 8 is the following: 1/2 kx squared, which is actually Hooke's law for spring constants. And as it turns out, this is a great potential energy operator to describe the vibrations of atoms. So if I have two masses on a spring, so recall there's force constant K. I know we're using the letters over and over again. So the force constant of the spring, or the spring constant, is K, and it is displaced over some distance x. So as it turns out, that 1/2 kx is a really nice potential energy operator to describe molecules and atoms. And we notice here in that operation, it still really is, there's no derivatives. It's granted it's not a constant because there's the x squared, but it's still just multiplication of this whole thing through. There's no derivative analysis, okay? What about the kinetic energy operator? Well, recall, I'm going to go back using this letter T because in some textbooks, the letter T is used for kinetic energy operator. And so recall, that was given as negative h bar squared divided by 2m. And remember, there's this second derivative function here, okay? And so now if I put these together, and I'm going to come back and talk about the second derivative in a moment, but if I put these both together to get total energy operator, that's where we use the Hamiltonian, okay, which would then be negative h bar squared 2m ddx squared plus 1/2 kx squared would become our total energy operator. When we operate that on a wave function, we need to get back an eigenvalue, a single valued constant. If we don't, then we have not used an appropriate wave function. Okay, so let's keep talking about this second derivative here, okay? So recall, the second derivative of a function is a measure of its curvature. So a large derivative indicates a sharply curved function. A sharply curved function is associated with a high kinetic energy, and one with a low curvature is associated with a low kinetic energy. So here is that kinetic energy operator. So here I wrote it as EK, but sometimes also T. I just want to get you all used to the various letters that are used in all the large number of texts on the subject. And so if we think about this, so this is kind of where we're also going to start to see some connection between this wave-particle duality, okay? So if we have this sharply curved function like this, okay, we see high curvature on this side, and we see high curvature on this side, all right? So there's a confluence. I'm going to draw arrows going either way, pointing, moving into that place, okay? And we note, of course, in the Born interpretation, we would say the most likely place is right here. And of course, there's no curvature at that point at all. Right at that top point, the slope is 0. Very interesting. We're going to come back to that. And then if we had this less steep function right here, okay, we can see there's lower curvature, lower kinetic energy than in this case. But all the same, we can still see that point there owing to a 0 slope will have physical significance in wave-particle duality. Another way we can think of this, the second derivative analysis, if we look at a wave function, perhaps it looks something like this, okay? So we can see as this oscillates and it gets to a higher and higher frequency, if we think about this kinetic energy going on, we have high kinetic energy on this side and low kinetic energy on this side, which would look something like this, right? So if my total energy is constant, then over to the right of this diagram, you can see there's a large kinetic energy and a small potential energy. But as we move to the left of this diagram and fixing the total energy, right, we could see the potential energy is in fact not constant through this diagram. Rather, it's changing. And so when we see something like this in our wave-particle duality, we would interpret this as a particle moving to the right. So in this reference frame right here, right, where let's say, this is my x-axis distance, this is 0, the origin. A wave function with curvature like this in our wave-particle duality would indicate, for one, a non-constant potential energy. And what that would actually give us, it would create a force on this particle, moving it in that direction indicated. Okay, very cool. So now that I think is a great place to cut it off for the week. These chapters in this section are big, so we still have a whole week to go on this chapter. I think I told you just only 2 more lectures, but I suspect that I might be putting this up into 3 shorter lectures. Okay, folks, I will see you later.